Mathematics are the result of mysterious powers which no one understands, which the unconscious recognition of beauty must play an important part. Out of an infinity of designs, a mathematician chooses one pattern for beauty's sake and pulls it down to earth. Pattern, a word that goes almost parallel with mathematics. But once in a blue moon, these patterns tend to break. Let me give you an example. The Polias conjecture, proposed in 1919, stated that more than 50% of the natural numbers will have an odd number of prime factors. So visualizing this should be pretty simple. Let's calculate the factors of a number, let's say 8. So 8 is 2 multiplied by 2 multiplied by 2. And we simply plot it. So let's just do this for all numbers from 1 to 10. Pretty easy so far. Now let's count the number of factors for each of these numbers. So let's just count the number of factors and write them all down in red. So 1 has 1 factor, 2 has 1 factor, 3 has 1 factor, 4 has 2 factors, and so on and so on. Now let me take all these red numbers that represent the number of factors and align them all in a box. Next, I'll just color the odd ones with orange and the even ones with blue. This representation tells me that I have 6 odd number of factors and 4 even number of factors up until the number 10. So from this I can infer that up until the number 10, the odd number of factors will always be greater than the even number of factors. But is this true only until the number 10? Well, Polya presumed that this rule was true until a particular number n. But the value of this number n hadn't been calculated up until 49 years later in 1958 when C. Brian Hazelgrove found a break in the pattern at a staggering number 1.845 into 10 raised to 361. To put that into some perspective, that number has 340 zeros more than the total amount of grain of sand present on Earth. But this wasn't the smallest number to break this pattern. A few years later, in 1980, Minoru Tanaka found the smallest number to break this Polya's pattern to be 906,150,257. So this is what is really interesting here. Something that continued a strict pattern up until 906 million or something suddenly tends to break. Who knew that a subject that is widely proclaimed to be boring would surprise you like that? But this isn't the only exception to a rather pattern-friendly subject. What if I was to tell you that a simple problem that even a 4th grader could understand hasn't been solved to this day, and the answer, if possible, would have to break the pattern just like the Polya's conjecture? So here is the problem, also known as the Collat's conjecture. Pick any number. Okay, let's say 7, because 7 is odd. We multiply it by 3 and then add it by 1, giving us 22. Now since 22 is even, we divide it by 2, giving us 11, which is again odd. So again we multiply it by 3 and add 1, 34, which is even. We divide it by 2, 17, then multiplied by 3, add 1, 52, divide by 2, 26, divide by 2, 13, odd again. So multiplied by 3 plus 1, 40, divided by 2, 20, again divided by 2, 10, divided by 2, 5. So now we are again at an odd number. We multiplied by 3, add 1, 16, divided by 2, 8, divided by 2 again, 4, again 2, and then eventually 1. Now that we have eventually come to 1, we multiplied by 3 and add 1, since 1 is an odd number, giving us 4, which again brings us back to 2 and 1, essentially keeping us in a recurring loop. But this is not just true for the number 7, rather all numbers calculated up until 2 raised to 68 rise and fall with a random order, but eventually come back to the same 4-2-1 loop. So if I was to create a connected chart for all the numbers according to this conjecture, it would create a sort of tree branch structure, but eventually ending at the bottom with 4-2-1. So now it seems like there is a certain rule or a pattern which makes us go back to this very loop, right? But the problem here is, even if not a single number has broken this rule yet, we cannot prove that all numbers up to infinity will eventually end up in this loop. So essentially we cannot prove it and we cannot disprove it. So when I refer to solving this question, I am referring to finding a number that either shoots to infinity or doesn't fall back to 1. So with use of modern computing, we found that all the numbers up to 295 quintillion, 147 quadrillion, 905 trillion, 179 billion, 352 million, 825,000 and 856 all fall back to 1. Now even with such high computing powers, solving this by brute force and calculating the conjecture for every number about 2 raised to 68 is still rather improbable. So given the complexity and persistence of the problem, it is challenging to predict when or if the Collatz conjecture will be solved. It may require an entirely new mathematical technique or breakthrough to determine its veracity. Mathematicians continue to study the conjecture, but until a definitive proof or counterexample is found, it will remain an open-ended question. Until that day, let this be the easiest unsolvable question in mathematics.